A short time ago, the James Webb Space Telescope, the most powerful one we have ever built, finally pointed its lenses at Alpha Centauri, the star system closest to our Sun. Scientists expected to find just ordinary stars shining in the darkness of space. But what the images revealed left many researchers speechless. Alpha Centauri is about 4 light-years away, which seems close in terms of the universe, but it would still take more than 70,000 years to get there with the spacecraft we have today. The information that came back showed things that nobody could explain properly, forcing scientists to ask questions they had never asked before. Could there be something in this neighbouring system that changes everything we thought we knew about the space around us? Get ready to fall asleep while listening to this video, and let your mind travel through this mystery. Subscribe to the channel, leave your like, and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. When the James Webb Space Telescope finally aimed its massive golden mirror at the closest stars to our Sun, the entire team of scientists and engineers behind the mission felt a mix of excitement and profound anxiety. This was the moment they had worked toward for decades, and the weight of expectation was almost palpable. Alpha Centauri, that bright point in the southern sky, is not one star but a system of 3. The 2 main stars, Alpha Centauri A and B, form a tight binary, dancing around each other, while the third, Proxima Centauri, a small faint red dwarf, orbits further out. Proxima Centauri had already made headlines years earlier with the discovery of Proxima b, a rocky planet nestled in the star's habitable zone, where temperatures might allow liquid water to exist. The possibility of life, even in its simplest forms, so close to us in cosmic terms, had captivated the public and the scientific community alike. But knowing a planet is there and understanding what it is like are 2 very different things. Before James Webb, our telescopes could only infer so much. We knew Proxima b was roughly Earth-sized and orbited its star every 11 days, but its atmosphere, its surface conditions, even its true mass were shrouded in mystery. The James Webb Space Telescope, with its unprecedented sensitivity in the infrared part of the spectrum, was built to lift that veil. This observation campaign was not a spontaneous decision. It was the result of years, literally years, of meticulous planning and fierce competition for telescope time. Scientists from around the world submitted detailed proposals, arguing why Alpha Centauri should be a prime target. The selection process was rigorous, because Webb's time is incredibly precious. The winning teams then embarked on a further phase of detailed design, deciding exactly how to use the telescope's powerful instruments. They had to choose specific infrared filters and observational modes on instruments like NIR spec and MIRI to tease out the faintest signals from the glare of the stars. The primary goal was clear: get a high-definition spectrum of Proxima Centauri b. A spectrum is like a chemical fingerprint. When starlight filters through a planet's atmosphere, gases present leave telltale dips in the light at specific colours. The hope was to detect signs of gases like methane, oxygen, carbon dioxide, or water vapour in combinations that might suggest biological activity. These are called biosignatures. But scientists were cautious. They knew a detection of oxygen alone doesn't mean life. It could be produced by non-biological processes, so the plan was to look for chemical imbalances, for pairs of gases that shouldn't coexist for long without something replenishing them. At the same time, the campaign aimed to study the entire Alpha Centauri system. For the binary stars A and B, the goal was to map their circumstellar debris disks. These disks are belts of dust, rocks and ice, leftovers from the planetary formation process. Studying their structure, composition and temperature would tell a story about how planets form and evolve in a double-star system. It could reveal if there were other, unseen planets shaping the disk through gravity. The expectations were monumental, but they were framed within the known laws of physics and astronomy. Everyone was hoping for revolutionary data, but data that would fit into and expand our current understanding of stellar and planetary science. No one was truly prepared for anomalies that defied explanation. The preparation involved simulating the observations thousands of times on computers. They had to account for the immense challenge of contrast. Proxima Centauri, though a dim red dwarf, is still vastly brighter than its tiny planet. Separating the light of the planet from the light of its star is like trying to see a firefly sitting on the edge of a blazing searchlight from thousands of miles away. James Webb uses a device called a coronagraph to block out the starlight, but it's not perfect. The teams practiced on simulated data, developing sophisticated algorithms to process the raw numbers that would come down from the telescope. They also coordinated with other observatories. Ground-based telescopes in Chile and Hawaii were scheduled to take simultaneous measurements in different wavelengths to provide context. Space telescopes like Hubble and TESS were also part of the broader campaign, though Webb was the star player. The launch and deployment of James Webb itself was a nerve-wracking saga that everyone remembers. After years of delays and cost overruns, seeing it unfold perfectly at Lagrange Point 2, a million miles from Earth, was a triumph. But for the Alpha Centauri teams, that was just the beginning. Commissioning the instruments took months, and then the long wait for their scheduled observation time began. During this period, the anticipation built not just among the scientists, but also in the public sphere. Articles speculated about what we might find. The idea of finding life next door was both thrilling and daunting. The teams held endless meetings going over every contingency. What if the data is too noisy? What if we see nothing at all? What if we see something ambiguous? They prepared for all outcomes. The psychological pressure was significant. Many of these researchers had dedicated their entire careers to exoplanet science. This observation could validate decades of work or leave them with more questions than answers. The sensitivity of James Webb promised to transform Alpha Centauri from a mere point of light into a characterized world or worlds. It promised to turn abstract concepts like habitable zone into concrete measurements of atmospheric pressure and temperature. For the first time, we might have been able to say if Proxima b had clouds, or if its atmosphere was thick like Venus or thin like Mars. The study of the debris disks around A and B was equally anticipated. In our own solar system, the Kuiper Belt and the asteroid belt tell the history of our planetary system. By studying the disks around these sun-like stars, we could learn how common or unique our solar system's architecture is. The teams were also looking for signs of other planets. The gravitational tug of unseen planets can create gaps and waves in the debris disks, so the images might reveal the presence of giant planets farther out. The preparation covered every detail, from the exact pointing of the telescope to the calibration steps needed after each observation. They even planned for solar storms and cosmic ray hits that could corrupt data. The data itself would take time to travel to Earth, then more time to be processed and analysed. The teams had a protocol for who would see the data first and how it would be verified before any announcement. This was to prevent false alarms and ensure the integrity of the science. The entire endeavour was a testament to international collaboration. Scientists from NASA, the European Space Agency, the Canadian Space Agency, and universities across the globe were involved. They shared models, debated strategies, and built a cohesive plan. The expectation was that this observation would be a cornerstone for future studies. It would inform the design of even bigger telescopes planned for the coming decades. It could potentially change our understanding of our place in the universe, but in a gradual scientific way. The mood was one of optimistic caution. They were ready for a slow, meticulous revelation of facts. They were prepared for the possibility that Proxima b might be a barren rock with no atmosphere, or that the debris disks might be boring and featureless. That would still be valuable science, ruling out possibilities and shaping theories. The historical context added to the weight. Alpha Centauri has been a target for dreamers and scientists for centuries, as the destination for countless science fiction stories about interstellar travel. Now, for the first time, we had a tool powerful enough to truly inspect it. The James Webb Space Telescope represented the peak of human engineering and curiosity. Turning it toward our nearest stellar neighbour felt like a natural historic step. The observation schedule was set. The commands were uploaded, the telescope slewed into position. On Earth, in control rooms and home offices, scientists waited. The data would take hours to arrive after the observation was complete. Those final hours of waiting were filled with quiet tension. They had done everything possible to prepare. They had thought through every scientific and technical angle. They were expecting to write new chapters in astronomy textbooks. They were expecting to maybe, just maybe, find hints that we are not alone. But they were also expecting the universe to follow the rules as we understand them. They were about to learn how naive that expectation was. The preparation was unprecedented, the expectation was immense. and the reality was waiting in the streams of infrared data, now travelling across the void toward our planet. The first data packets arrived, a torrent of ones and zeros that were meticulously reconstructed into images and spectra. The initial processing was a routine affair, a well-rehearsed dance of calibration and correction that the teams had run countless times on simulated data. The first targets were the debris disks around Alpha Centauri A and B, and the images that formed on the screens were breathtaking in their clarity, revealing intricate details that would take months to fully interpret. But the moment of truth was the dataset for Proxima Centauri B. The teams used a technique called transmission spectroscopy. They didn't try to image the planet directly, that was still too hard, but instead watched for the tiny dip in the star's light as the planet transited, passing in front of Proxima Centauri. During that transit, a sliver of starlight would shine through the planet's atmosphere, if it had one, imprinting its chemical signature. The data reduction pipeline churned, subtracting the immense stellar signal, correcting for the star's own activity, and isolating the minuscule fingerprint of the planet's atmospheric gases. The first spectra looked odd. There were dips and wiggles in the light curve that didn't correspond to any known atmospheric model. At first, the assumption was noise, an artifact of Proxima's notorious stellar flares. But as they combined multiple transit observations, the anomalous signal didn't average out. It persisted, and its properties became more defined. It wasn't a set of discrete absorption lines from gases like water or carbon dioxide. Instead, it appeared as a broad, subtle dimming across a specific range of infrared wavelengths, a dimming that seemed to warp the very shape of the transit light curve itself. In the most advanced visualizations, which attempted to reconstruct a crude map of the planet's terminator line, the border between day and night, this effect manifested not as a feature of the atmosphere, but as a distortion in the silhouette of the planet against the star. It was as if the planet's limb was subtly frayed, or shrouded by something that absorbed light in a non-linear, non-uniform way. They called it the shadow signature, for lack of a better term. It wasn't a cloud, because clouds, whether of water or silicate particles, have predictable scattering properties. This absorbed light in bands that didn't match the vibrational modes of any known molecule. It wasn't a coronal mass ejection or stellar weather from Proxima, because the effect was localized precisely to the planetary transit and its immediate vicinity. The shadow seemed to cling to the planet. The spectral signature was unique and deeply unsettling to the spectroscopists. In normal spectroscopy, you expect sharp lines or broad bands. This was different. It was as if the light was being processed or filtered through a medium that had a complex, almost algorithmic response to different wavelengths. One scientist described it as seeing the diffraction pattern of an engineered material, not the absorption spectrum of a natural gas. The initial reaction was, of course, to doubt the instrument. They ran every diagnostic. They checked for contamination from cosmic rays hitting the detectors. They checked the alignment of the telescope's mirrors. They even checked for the possibility of an unknown debris cloud in the Proxima system passing in front of the star at the same time as the planet. Every check came back negative. The signal was real, and it was coming from the immediate environment of Proxima Centauri B. Then they turned to natural astrophysical explanations. Could it be an immense, never-before-seen type of aurora, wrapping the planet in a shroud of energetic particles? The energy requirements would be staggering, far beyond anything generated by stellar wind interaction, even from a flare star like Proxima. Could it be some form of exotic geology, a planet-wide volcanic haze of unknown composition? The stability and spectral shape were wrong. Volcanic aerosols are messy and varied, not coherent and structured. Could it be a swarm of moons or rings? The shadow's spectral properties were inconsistent with simple solid body occultation or reflected light. Each hypothesis was formulated, modelled, and discarded. The shadow signature defied replication in their computer simulations. It wasn't merely an unknown, it was an unknown that behaved in a way that seemed to contradict basic principles of how matter and light interact. The most advanced atmospheric modelling suites used to simulate the climates of exoplanets hit a wall. You could not input natural conditions and get this output. A cold fear began to seep out of the data analysis rooms and into the wider team. This was not the gradual revelation of facts they had prepared for. This was a hard left turn into the inexplicable. The shadow signature was the first concrete piece of a puzzle that didn't fit the picture onto the box. It was an anomaly that resisted all immediate attempts at categorization, and in science, an anomaly that persistent and that clear is either a mistake or a revolution. They had ruled out mistake. The implications began to dawn on them slowly, then all at once. If it wasn't natural, then what was it? The word artifact was used cautiously, and not in the sense of a data glitch, but in the sense of an artificial object or phenomenon. Could it be some form of megastructure? A thought that had been confined to science fiction and fringe astronomy papers now sat in the middle of their peer-reviewed data reduction software. The idea of a Dyson swarm or a planetary scale energy collection array was floated, but even that didn't quite fit. Those concepts predicted a different kind of signature, usually an excess of infrared waste heat, not this precise wavelength-dependent shadowing. This was something else, something that seemed to interact with light itself in a refined, perhaps optimized manner. Perhaps the most frightening aspect was the signal's coherence. Natural systems are noisy. They have variations, statistical fluctuations. This signature had a quiet, precise and repeatable quality to it. It showed up in every single transit observation with the same core features, as if it were a permanent engineered fixture. It suggested stability and purpose, two words that make planetary scientists very nervous when applied to non-biological phenomena. The teams fractured slightly under the weight of the discovery. Some insisted on burying themselves in more data, seeking a natural explanation at all costs. They proposed ever more complex models involving novel chemistry or physics. Others began quietly and then more openly to discuss the possibility that they were looking at technology. The shift in mindset was jarring. These were astronomers, astrophysicists, data analysts, people trained to think in terms of billions of years, gravitational forces and nuclear fusion. Now they were forced to consider engineering, intention and design. The shadow signature was not alive, but it hinted at the presence of something that could build, that could manipulate matter on a planetary scale. The scare factor came not from a dramatic image of alien cities, but from this subtle, abstract fingerprint in a graph. Its very subtlety was what made it so credible and so terrifying. A blurry picture of a pyramid on Mars can be dismissed as pareidolia, a mathematically persistent anomaly in a calibrated spectrum from the most advanced telescope ever built cannot. It demanded an explanation that their current science could not provide. Meetings became tense, hushed affairs. The normal collegial debate turned into something more charged. Careers, worldviews, and the future of human civilization seemed to hang on the interpretation of a few pixels of data. The protocol for verification was stretched to its limits as they brought in external experts, sworn to confidentiality, to examine the data. The consensus among these outsiders was the same. Instrumental error was highly unlikely. A natural astrophysical origin was not currently supported by any known model. They were left with a void, and the human mind abhors a vacuum. That vacuum began to fill with a slow dawning realization of insignificance. The principle of mediocrity, the idea that Earth and humanity are not special, was a comforting foundation for modern astronomy. It implied that the universe operates by uniform rules, and we are a typical product of those rules. The shadow signature threatened that. It suggested that Proxima Centauri b was not typical. It was peculiar in a way that was profound and directed. The scientists felt a chill that had nothing to do with the temperature of the server rooms. They had trained for years to find life, perhaps even simple biosignatures. They were psychologically prepared for that, or so they thought. They were not prepared for this, an enigma that spoke not of biology, but of technology so advanced it manifested as a fundamental distortion in their data. It felt like they had been peering through a keyhole, expecting to see a room, and instead saw an eye looking back. The shadow was passive, but its very existence felt like a sign. The next phase of the investigation was fraught with a new kind of tension. Every additional observation of Proxima b was now scrutinized for further clues about the shadow. They tried different infrared wavelengths, hoping to map its extent and properties. They found it was not uniform. It had structure, faint gradients that suggested it might be thicker in some areas than others. It seemed to be tied to the planet's rotation, indicating it was anchored to the surface or a specific orbital location. The scare deepened when they correlated the shadow's properties with the planet's orbital phase. There was a hint, just a hint, that the shadow's spectral signature changed very slightly when the planet was at different points in its orbit, as if it were responding to the varying intensity of stellar radiation. This was no longer just a strange static phenomenon. It appeared to be a dynamic one. The scientists were now truly scared. They had discovered something that was not just unknown, but seemingly responsive. The data stream from James Webb, which had begun as a river of discovery, now felt like a flood of questions with no answers in any textbook. The world outside the collaboration remained blissfully unaware. Press officers held the line, citing the need for thorough peer review. But inside, the atmosphere had changed from one of excited exploration to one of cautious and deeply anxious investigation. They had looked into Alpha Centauri, expecting to see a mirror of our own solar system, or at least a familiar canvas of natural processes. What they saw first was a shadow that refused to be explained, and that shadow cast a long, cold darkness over their expectations and over their perception of humanity's place in the cosmos. The precedent had been set. The first anomaly was on the board, and it had scared them. It meant that whatever else James Webb would find in this system, it would not be business as usual. The universe next door was no longer just a physical space. It had become a puzzle box, and they had just found the first piece that didn't fit, a piece that suggested the box itself was constructed by intelligence. With the unsettling mystery of Proxima B's shadow signature still hanging over them like a pall, the science teams urgently pivoted the mighty telescope's gaze toward the brighter, sun-like stars of the binary pair, Alpha Centauri A and B. If the red dwarf's planet held bizarre secrets, perhaps the more familiar stellar environments would provide comforting, normal data. The initial focus was Alpha Centauri A, a star near twin to our Sun. A key observational target was its circumstellar debris disk. Every star with planets has one, a broad, messy belt of dust, rock and ice left over from the planet-forming process, constantly replenished by collisions among asteroids and comets. Our own solar system has one, the Kuiper Belt. Scientists expected to see a faint, fuzzy, elliptical halo of warm infrared emission round Alpha Centauri A, slightly brighter in the middle and fading at the edges, perhaps with a few clumps or gaps hinting at the gravitational influence of unseen planets. They pointed the mid-infrared instrument, MIRI, and began the long, painstaking exposures needed to tease its faint glow from the stellar glare. When the processed images finally coalesced on the screens, the reaction was not the quiet satisfaction of a hypothesis confirmed, but a stunned collective silence, followed by a murmur of confusion that quickly swelled into uproar. The debris disk was there, but it was not a smooth, featureless haze. It was structured. Not just structured, but geometrically structured in ways that defied every model of natural astrophysical formation. The disk appeared as a broad ring, but within that ring, the infrared emission was not continuous. There were distinct, sharply defined regions of incredibly low dust density, creating what looked like voids or gaps. But these were not the simple, cleared-out gaps a single large planet might create, like Saturn's rings. These voids were symmetrical. They formed patterns. Some analysts saw what appeared to be a series of concentric, equally spaced gaps, like ripples in a pond frozen in time. Others identified radial spokes of clearer paths, regions where the dust seemed to have been systematically scoured away, leaving dark channels that extended from the inner edge of the disk outward. The most shocking features, however, were the concentrations. In the expected chaotic jumble of a debris disk, dust and planetesimals cluster randomly from collisions. Here, the warm material was gathered into precise, compact knots, and these knots were not randomly placed. Several were located precisely at the Lagrange points of the system. Lagrange points are gravitational sweet spots, where the pull from Alpha Centauri A and its binary partner, Alpha Centauri B, balance out. Objects can reside there stably. It's natural to find some dust there, but to find such massive bright concentrations specifically, and only at these points, and in a pattern that mirrored mathematical predictions of stability, was absurdly improbable. It looked less like an accidental gathering and more like material had been deliberately parked there. The immediate instinctive response was to blame the instrument or the processing algorithms. They had worked so hard to remove artifacts that maybe they had created them. They reprocessed the data from the rawest level, using different teams and independent software pipelines. The structures remained. They checked for contamination from background galaxies or instrumental diffraction spikes. Nothing accounted for it. They had to accept the image was real. Then began the frantic search for a natural explanation. Could a swarm of undiscovered planets, each with complex resonances, sculpt such a perfect pattern? They modelled it. To create such geometric precision would require a fleet of planets of just the right masses and just the right orbits, a configuration so finely tuned it would be unstable over astronomical timescales. The gravitational dance would inevitably decay, erasing the patterns within millions of years, a blink of an eye compared to the system's age. Could it be the effect of Alpha Centauri b, the binary companion? They modelled that too. The gravitational influence of the other star does stir the disk, but it creates spiral arms and broader symmetries, not razor-sharp concentric rings and precise Lagrange point accumulations. The natural forces at play are chaotic and smoothing. They do not create this kind of crisp, ordered architecture. One scientist compared it to walking into a forest and finding the trees planted in perfect rows and columns. You could maybe, with immense stretch, imagine a bizarre natural event causing it once, but the maintenance of that order over time is the real miracle, and this disk was old. These structures, if natural, would have needed to persist for billions of years. The probability calculus became a central grim focus. Teams of statisticians were brought in. The likelihood of such symmetrical voids and such perfectly placed knots arising from random collisions and gravitational interactions was, in the words of one report, indistinguishable from zero. It was not just unlikely, it was effectively impossible within the standard model of debris disk physics. With natural causes receding into the realm of the fantastically improbable, the unthinkable alternative had to be confronted directly. The patterns in the disk did not look like nature, they looked like engineering. The voids resembled swept areas. The concentric gaps hinted at large-scale construction projects moving through the disk, clearing material in waves. The Lagrange point accumulations were the clincher. In theoretical papers on advanced civilizations, Lagrange points are highlighted as prime real estate. They are stable, energy-efficient locations to park things, space stations, shipyards, manufacturing hubs, or energy collectors. The material gathered there in the Amiri images was warm, emitting in the infrared. It wasn't just cold rock, it was material that had been processed, perhaps by construction activity, absorbing sunlight and re-radiating the heat. The term mega-engineering entered the secure collaboration chats, first with ironic scare quotes and then without them. The concept of a Dyson sphere, a hypothetical structure enclosing a star to capture its energy, has many variants. One of the less extreme versions is a Dyson swarm, a vast collection of independent orbiting collectors. The early stages of building such a swarm would look a lot like this. Organised activity in a debris disk, harvesting raw materials. The symmetric gaps could be mining zones stripped clean of useful asteroids. The Lagrange point knots could be construction nodes or resource depots. The scale was incomprehensible. This wasn't about building a city or even a continent-sized object. This was about systematically altering the infrastructure of an entire solar system and repurposing its leftover planetary building blocks into something else. The fear that began with Proxima B's shadow transformed into a deeper, more profound dread. The shadow was a mystery, an anomaly. This was a blueprint. This was evidence of activity, of a project. It was not a static, perhaps ancient artifact. The thermal signatures suggested ongoing, or at least geologically recent energy use. They were looking at a construction site that was light years across. The psychological impact on the researchers was severe. Studying a weird atmospheric phenomenon was one thing. Staring at what appeared to be the organised industrial-scale alteration of a star system was another. It made humanity's greatest engineering achievements, the International Space Station, the Large Hadron Collider, look like sandcastles on a beach. The sheer ambition and capability implied were humbling to the point of horror. Discussions turned practical and terrifying. If this was mining and construction, who was doing it? Were they still there? Was this an ongoing project or an archaeological relic? The debate raged. Some argued the structures were ancient, a fossil of a bygone civilization that had either moved on or died out. Others pointed to the specific thermal signatures. The materials seemed to be at a temperature that suggested they were not just passively sitting in sunlight, but might be internally active. Could they be automated? A self-replicating swarm of machines set in motion eons ago, still dutifully converting a star system into something. The term berserker was whispered, referencing old tales of malevolent robotic probes. But there was no evidence of malice, only evidence of immense indifferent activity. The most unsettling conclusion was one of quiet occupancy. Alpha Centauri was not an empty system waiting for explorers. It was an occupied system, and the occupants, whether biological or artificial, worked on a scale that rendered human concepts of territory and property laughable. They don't care about planets, the thinking went. They care about resources, energy and structure. The debris disk isn't a historical relic to them, it's a lumberyard. This discovery framed everything else. It provided a grim context for the shadow around Proxima b. If a civilization could re-engineer a debris disk, what might it do to a planet? Perhaps the shadow was a side effect of some planetary-scaled project on Proxima b, a piece of technology so large it subtly warped the light passing by the planet. The ordered disk of Alpha Centauri A shattered any remaining hope that the anomalies were isolated or explainable by some new physics. This was pattern, intention, and power written across the heavens in letters of warm dust and empty space. The teams now faced a crisis of communication far greater than before. How do you tell the world you might have found not just life, but a stellar-scale construction project next door? The data was in some ways more vulnerable to skepticism than the spectral shadow. A critic could say the image processing created artifacts, or that their models of natural disk dynamics are incomplete. But for those living with the data day and night, the conclusion was inescapable. They had pointed the most advanced telescope ever built at the most sun-like star nearby, hoping to see a familiar disk of dust. Instead, they saw a fingerprint of intelligence so vast it used asteroids as bricks and then gravitational balance points as foundations. The universe had ceased to be a purely natural realm. The system next door was managed. The structured disk around Alpha Centauri A dominated the conversation for weeks, a silent, staring puzzle that refused to be solved. But as the teams continued their scheduled observations, gathering data not just in images but in continuous spectroscopic readings, another anomaly emerged from the noise. This one was not a static structure but a dynamic signal. It appeared in the data streams from the most sensitive infrared detectors, the ones designed to catch the faintest whisper of heat from the edge of the universe. What they caught was a series of pulses. They were not coming from the roiling surfaces of the stars. They were not the predictable broadband flashes of a stellar flare from Proxima. These were different. They were sharp, ultra-narrow bursts of infrared radiation, like the precise ticks of a metronome set against a background of cosmic static. The pulses originated from fixed points in the emptiness of space within the Alpha Centauri system itself, specifically in the vast gulf between the A and B stars. They came from nowhere, and from specific nowheres. The initial assumption, naturally, was some form of instrumental glitch or a cosmic ray hit, but the signature was all wrong for that. Cosmic rays leave a specific, messy fingerprint across the detectors. These were clean, spectral lines that appeared and disappeared with a rapid, repeatable cadence. They were real photons arriving from a specific direction. The first step was to triangulate. Using the precise pointing data and the telescope's own motion, they pinned down the sources. The pulses weren't coming from a planet or a visible object. They emanated from seemingly empty points in space, locations that corresponded to gravitationally stable zones, like Lagrange points, or other otherwise unremarkable coordinates in the interstar void. Each pulse had a specific energy, a very particular infrared colour, and they repeated. The pattern was the next focus. Was it random? Teams of signal processors and mathematicians, some of whom had worked on SETI, the search for extraterrestrial intelligence, descended on the data. They ran every analysis for periodicity. The intervals between pulses were not random noise, but they didn't match a simple repeating clock signal either. It wasn't a sequence of prime numbers or a blast of pi. It was more complex, a pattern that seemed to have layers, perhaps a carrier wave with a modulated signal on top. The structure hinted at encoded information, but a codex they lacked. The pulses were directional. This was a critical finding. They weren't a general broadcast in all directions like a star's light. Further analysis of the slight Doppler shifts and intensity variations suggested the beams were tightly focused, aimed from one specific point to another. It was the difference between a lighthouse sweeping the horizon and a laser pointer aimed at a single window. This focus implied intent and efficiency. You focus a signal when you are trying to communicate with a specific receiver, or when you're scanning a specific area, like a radar. The energy required to create such sharp, focused pulses of infrared across interstellar distances within a system was significant, but not unimaginable for a civilization capable of re-engineering debris disks. It was the precision that was breathtaking. The immediate task was to rule out every natural phenomenon. Could these be some bizarre form of pulsar? No, pulsars are neutron stars and emit across the electromagnetic spectrum, not in focused infrared beams from empty space. Could they be collisions between small, dark objects like asteroids? Such collisions would produce a flash, but a messy broad-spectrum one, not a series of identical narrow-band pulses from the same spot. Could it be some unknown atmospheric phenomenon on a rogue planet? The pulses originated in deep space, far from any known planetary body. What about the stars themselves? Perhaps some form of resonant stellar oscillation? The frequencies and the fixed non-stellar locations ruled that out conclusively. Each natural explanation was systematically dismantled. The pulses were artificial in the most literal sense. They exhibited characteristics of an engineered signal. They were efficient, information-rich, and targeted. The realization that they were likely looking at active signaling or scanning technology within the system was a watershed moment that dwarfed even the discovery of the structured disk. The disk could have been ancient, a fossil. The pulses were happening now, or at least they had happened whenever the light now hitting James Webb's mirror left Alpha Centauri, roughly 4 years ago. This was present tense activity. The system was not a quiet museum, it was a busy place with traffic. The scientific term technosignature was now the official hush term used in the confidential reports. They had found one. The implications were staggering and terrifying. First, it meant the intelligence in the system was not extinct. It was active, communicating or operating machinery. Second, the use of infrared was deeply instructive. For decades, human SETI efforts had focused almost entirely on radio waves, thinking an advanced civilization would use that for communication. The Alpha Centauri system, according to the broader JWST data, was oddly quiet in traditional radio bands. Now they knew why. This civilization, if that's what it was, had moved beyond radio. Infrared light, as a communication medium, has advantages. It has a much shorter wavelength than radio, which allows for tighter focus and higher data rates. It's also less likely to be drowned out by the natural radio noise of stars in the galactic background. It was a more sophisticated, more efficient technology. We had been listening on the cosmic equivalent of a tin can telephone, while they were using fibre optic cables. The pulses also suggested a level of infrastructure. You don't have tight beam communications between random points in space unless you have things at both ends to send and receive. Those fixed coordinate sources likely weren't the endpoints themselves, but waypoints, or the beams passing through a specific point in space. It hinted at a network, a web of communication links connecting various stations, habitats, or ships across the star system. The idea of a solitary probe or a single megastructure vanished, replaced by the image of a bustling, interconnected civilization occupying the entire volume of the triple star system. The most frightening analysis came from the military consultants quietly brought into the loop. They looked at the pulse patterns and the directional data and offered a grim assessment. The pattern they suggested didn't look like a simple hello beacon. Beacons are designed to be found and understood. This pattern was complex, modulated, and targeted. It looked like operational traffic, internal communications. Or, given the scanning-like regularity of some of the sequences, it could be a form of LiDAR, light detection and ranging, but on a stellar scale. They might be mapping their own system with incredible precision, or scanning the space around them for incoming objects. The thought that our James Webb telescope might have just been lit up by an alien security LiDAR sweep, a brief ping of infrared that registered our observation as a new, subtle reflection from 4 light-years away, was a chilling one. It meant we might have just rung the doorbell by staring through the window. The ethical and strategic dilemma which had been theoretical, became horrifyingly immediate. The pulses changed the question from "are we alone" to "have we been noticed?" The very act of detection might have been a two-way event. The teams now faced data that was no longer just observational, it felt interactive. Every new observation schedule was debated with paranoia. Should they stare longer at the pulse sources to decode the pattern, risking drawing more attention? Or should they look away, pretend they saw nothing? The data was also a key to the other mysteries. Scientists began cross-referencing the pulse coordinates with the other anomalies. Did any pulses originate from near the structured disk's Lagrange points? Yes, some did. Did any seem to be aimed in the general direction of Proxima b? The analysis was inconclusive but possible. The pulses were the nervous system of the system, and they were now seeing its faint infrared heartbeat. The psychological effect was profound. Before, the evidence was architectural, like finding the ruins of Machu Picchu on Mars. Impressive, but static. The pulses were like finding the lights on, and hearing whispers in the ruins. It injected a visceral, immediate fear into the scientific process. The universe felt suddenly crowded, and the neighbours were not just home, they were having a conversation on a channel we could barely perceive. The knowledge that such technology operated a mere 4 light-years away rendered human spaceflight ambitions simultaneously quaint and perilous. A journey that would take our fastest probes tens of thousands of years was, for them, likely a routine trip. Our solar system was not an isolated oasis, it was a suburb of an active metropolis. The final, humbling conclusion was about our own technological adolescence. For over a century we've been leaking radio and television signals into space, a growing bubble of noise announcing our presence. We always imagined more advanced civilizations would do the same, louder and prouder. The Alpha Centauri pulses taught us the opposite. Advanced technology may not be loud. It may be precise, efficient, and discreet. It uses the minimum necessary energy, focused exactly where it needs to go, leaving almost no wasteful leakage for eavesdroppers like us to find. We found it only because we built an instrument of exquisite sensitivity looking in the right part of the spectrum, almost by accident. It suggested a galactic culture might be a quiet, hidden network of narrowband signals invisible to the noisy, blundering civilizations just learning to shout. We had not found a shout. We had found a whisper, and in that whisper was the sound of a technology so far ahead of us that it made our greatest achievements seem like the first spark from a caveman's flint. The scare was no longer about what they were, it was about what we were not, and what we might never be allowed to become. The discovery of the structured disk and the pulse communications network painted a picture of staggering activity, but it was all circumstantial, evidence of engineering on a scale that baffled the mind. The real hammer blow, the one that shifted the conversation from "there's technology there" to "something is actively living there," or "something is being meticulously maintained," came from the original primary target, the atmosphere of Proxima Centauri b itself. All other data was context, but this was a direct chemical interrogation of a world in the habitable zone. The teams had finally processed and reprocessed the transmission spectra. The starlight filtered through the planet's air during its transits. The initial confusing data from the early days, overshadowed by the shadow signature, was now clarified with more observations and sharper analysis. What it revealed was not just an anomaly, it was an impossibility. The first shock was the detection of molecular oxygen and methane together in significant abundances. On Earth, that combination is a classic biosignature. Oxygen is highly reactive, it wants to bind with other elements. Methane is also fragile in an oxygen-rich environment. Finding them coexisting in stable quantities in an atmosphere suggests something is constantly replenishing them, like photosynthesis producing oxygen and microbial life producing methane. For a brief, euphoric moment, some on the team dared to hope they had found simple planet-wide life. But that hope vaporized as the rest of the spectral lines came into focus. The oxygen wasn't just any oxygen. The isotopic ratios were all wrong. Elements come in different isotopes, atoms with the same number of protons but different numbers of neutrons. In nature, certain processes favour lighter isotopes over heavier ones. The oxygen in Earth's atmosphere has a specific fingerprint of these isotopes, a result of biological and geological history. The oxygen around Proxima b had a fingerprint that was not just different, it was purified. The heavy isotopes were present in ratios that suggested a separation process far more efficient than any natural planet could achieve. It was the kind of isotopic signature you might expect from industrial-scale air processing, not from forests or algae. The methane told a similar story. It wasn't just methane. Attached to its molecular structure were traces of deuterium, a heavy isotope of hydrogen, in a pattern that didn't match any known abiotic production method, like serpentinization in hydrothermal vents. It looked engineered. Then came the real showstopper, atmospheric stability. Proxima Centauri is a flare star. It frequently unleashes titanic bursts of radiation and charged particles that would, by all rights, strip away the atmosphere of a close-orbiting planet like Proxima b over a few 100 million years. Even if an atmosphere persisted, these flares would chemically tear it apart, breaking molecules like oxygen and methane apart, ionizing gases, and creating a chaotic oxidizing mess. The models were clear. A terrestrial planet in that orbit without a massive magnetic field should have either no atmosphere or a thin, chemically battered one dominated by carbon dioxide or heavy noble gases. Proxima b's atmosphere, according to the James Webb data, was none of those things. It was thick, complex, and in a state of profound thermodynamic non-equilibrium. It was stable. Not just a little stable, but implausibly, perfectly stable. The chemical constituents were not reacting with each other or being destroyed by stellar radiation at the rates they should have been. It was as if the atmosphere existed inside a protective bubble, a shield that mitigated the worst effects of the stellar flares. The data hinted at this directly. There were spectral features suggesting an abundance of charged particles in the upper atmosphere, but arranged in a layered, structured way, not the chaotic soup of a planet being constantly bombarded. It looked less like a natural magnetosphere and more like an active field, a kind of planetary defense grid dissipating stellar energy with eerie efficiency. The final nail in the coffin of natural explanations was the presence of trace gases that simply don't belong together. There were whiffs of complex hydrocarbons and nitrates in concentrations that suggested an industrial, not a biological origin. Imagine detecting the spectral signature of refined plastics or specific fertilizers in the global air of another world. That was the level of strangeness. The atmosphere of Proxima b was not a product of geology or biology as we know it. It was a carefully maintained composition. The conclusion was inescapable. The atmosphere was managed. It was being kept in a specific life-friendly state against the natural destructive forces of its star. This was terraforming, or more accurately, planetary atmospheric engineering in real time. Someone or something was gardening the planet. The implications were more intimate and more terrifying than the megastructures. The disk and the pulses spoke of a civilization's infrastructure. The atmosphere of Proxima b spoke of its home, or perhaps its zoo or its garden. It showed not just capability but care, or at least deliberate maintenance. This wasn't a random artifact. It was an ongoing project to sustain a specific environmental condition. The question of why was paralyzing. Was it for biological inhabitants? If so, were they native to the planet or were they transplants? Or was the atmosphere being maintained for some other reason? Perhaps to support a vast planetary-scale biosphere that was itself a machine, or to preserve some resource, or even as a kind of museum piece or ecological preserve. The very fact of the management suggested a long-term perspective spanning millennia, the patience to continually counteract a star's violence to keep a world in a specific, seemingly gentle state. This finding reframed the shadow signature from a mysterious anomaly into a potential component of this planetary management system. Perhaps the shadow was a side effect of the shielding technology, a byproduct of whatever field or structure was protecting the atmosphere and surface from Proxima's flares. The planet wasn't just inhabited, it was cocooned. For the scientists, this was the most profound moment of existential dread. Finding ruins or even active machinery is one thing. Finding a carefully tended world, a planet with its climate controlled by forces beyond comprehension, made the universe feel owned. It made Earth feel like a wild, unkempt lot next to a meticulously manicured estate. The sheer normalcy of the atmospheric composition, the oxygen, the methane, was now the most alien thing of all. It wasn't natural normalcy, it was artificial normalcy, a perfect replica of a biosphere's signature imposed and maintained by technology. It meant that what we consider the hallmark of life could be fabricated. It blurred the line between a living world and a potted plant on a cosmic windowsill. The debate about contacting the system became even more fraught. If they were maintaining a planet's atmosphere, they were undoubtedly monitoring it with extreme precision. Would they notice the tiny anomalous spectral lines caused by Earth's telescopes observing them? Almost certainly. Our observation might already be logged as a minor anomaly in their planetary stewardship data. The idea of sending a signal felt like shouting at the groundskeeper of a vast ancient estate. The scientific fallout was immediate and revolutionary. Astrobiology textbooks were now incomplete. The search for life could no longer just look for chemical imbalances. It had to look for chemical imbalances that were too perfect, too stable, too isotopic. It had to differentiate between a naturally evolved biosphere and a managed one. The very definition of a habitable zone planet changed. Habitability might not be a gift of orbital distance alone, but a condition enforced by technology. Proxima b, by natural rights, should be a barren, irradiated rock. Instead it was an oasis, and that oasis was clearly, undeniably artificial. The fear transformed from a fear of the unknown to a fear of understanding just enough to recognise our own insignificance. We weren't looking at a peer civilization. We were looking at gardeners who treated stellar flares as a minor nuisance to be corrected, who purified atmospheres on a planetary scale, and who possibly viewed an entire world as a project. The quiet, maintained atmosphere of Proxima Centauri b was the most deafening statement the telescope had received. It said, "This is not your universe, it is curated," and that changes everything. The mind-bending realization that Proxima Centauri b's atmosphere was a carefully maintained artifact sent scientists scrambling to examine every other piece of data with new, terrified eyes. If a planet could be groomed, then what about the raw materials of the system itself? The investigation expanded from planets and structured disks to the most fundamental level, the chemical composition of the dust. Not the large structures, but the diffuse microscopic grains floating in the circumstellar environment around all three stars. Using the telescope's most sensitive spectrometers, they conducted a comprehensive inventory of the Alpha Centauri system's dust, analysing the infrared light it emitted to determine its elemental makeup. This was routine astrophysics. The composition of dust tells the story of a system's formation and history. They expected to see a familiar cosmic abundance. Lots of silicon, magnesium, iron, oxygen, and carbon. The common stuff of rocks, sand, and soot that makes up our solar system's dust and every other observed system. The results were not familiar. They were profoundly, disturbingly skewed. The data revealed a glaring deficiency. Elements that should have been dominant were barely present. Silicon, the fundamental ingredient of sand, rock, and the very crusts of terrestrial planets, was almost absent from the fine, warm dust populations in the inner system. It wasn't just low, it was anomalously depleted. The same went for iron and nickel, the core metals of planets. It was as if someone had gone through the system with a cosmic magnet and a sieve, systematically pulling out these foundational materials. In contrast, other elements showed surprising relative enrichment. Certain rare earth elements, ones with names like lanthanum and neodymium, along with specific refractory metals useful in high-tech applications, were present in the dust at concentrations that made no geological sense. These elements are rare in the universe. They form in specific, violent stellar processes and are normally scattered in trace amounts. Here they were concentrated. The pattern was the exact opposite of natural fractionation. Natural processes, like heating, cooling, or stellar winds, sort elements based on volatility or weight. They don't meticulously remove all the silicon and iron while leaving behind and concentrating the technologically useful rare stuff. This was a signature of selection, of sorting. The team spent months trying to model a natural cause. Could intense radiation from the stars selectively vaporize some elements and not others? The physics didn't support it. The missing elements were not uniformly more volatile. Could it be that the dust was not primordial, but the ground-up remains of peculiar silicon-poor asteroids? That would require the entire asteroid population of the system to be made of exotic, unheard-of material, which was statistically nonsense. Every natural model failed to produce the stark, targeted depletion they observed. The silicon gap, as it became known, was a chemical ghost town. With natural causes becoming untenable, the only remaining hypothesis was as unsettling as it was simple: mining. Not mining in the human sense of digging pits on a planet, but mining on a stellar system scale. The systematic removal of bulk raw materials, silicon for construction, iron and nickel for structural support, from the accessible reservoirs of dust and small planetesimals. The concurrent enrichment of strategic rare elements suggested these were either byproducts of the mining process that were being concentrated in waste piles, or perhaps they were the specific target of a later, more refined harvesting operation. The scale of the operation was what induced vertigo. To deplete the fine dust of an entire star system of its silicon requires processing volumes of material that are incomprehensible. It means harvesting not just a few asteroids, but millions of them, grinding them down, extracting the desired elements, and somehow removing or using the leftovers. The energy and logistics involved dwarf anything human civilization has ever contemplated. It implied automated factories working for millennia, maybe millions of years, slowly converting the non-essential mass of a star system into something else. This was the Pedrera Cosmica, the cosmic quarry, concept made terrifyingly real. The system wasn't just occupied, it was being consumed, repurposed at a molecular level. The structured disk around Alpha Centauri A now had a clearer purpose. Those geometric gaps and cleared zones weren't just mysterious patterns, they were likely active or legacy mining sites, areas where raw material had been thoroughly extracted. The Lagrange point accumulations could be processing stations or storage depots for refined materials. The entire system, from its managed planet to its missing silicon, pointed to a civilization that viewed a star system not as a collection of worlds to live on, but as a reservoir of matter and energy to be utilised according to a grand design. The implications for human technology were immediate and humbling. Our entire technological civilization is built on the silicon microchip and steel alloys. We are, at our core, a silicon and iron-based technological species. The Alpha Centauri system's inhabitants, it appeared, had moved far beyond that. Their technology, implied by the elemental signatures, seemed to rely on different, perhaps more advanced materials. They had so thoroughly harvested the basic stuff of our tech that it was scarce in their environment. It was like visiting an advanced city and finding no trees or stone, because they had long ago progressed to composite materials and recycled everything. The scarcity was artificial because it was the result of consumption, not nature. This also provided a grim, logical reason for expansion. If a civilization grows to consume the bulk materials of its home system, it might need to look elsewhere for more. Alpha Centauri is, in cosmic terms, right next door. The thought that our solar system, rich in untouched silicon, iron, nickel, and water, might represent a valuable unclaimed resource deposit to a culture with such capabilities was a stark and frightening geopolitical reality on a galactic scale. It reframed the fear from one of mere contact to one of potential economic interest. We might not be neighbours, we might be a mineral claim. Furthermore, the cleanliness of the operation was telling. Apart from the structured dust, there was little obvious pollution or waste. The system was tidy. This suggested not just advanced technology, but advanced environmental management on a system-wide scale. They weren't leaving behind slag heaps. They were efficiently using or sequestering byproducts. This level of control was perhaps more impressive than the mining itself. The discovery of the silicon gap forced a complete re-evaluation of what we look for when scanning other star systems. Anomalously low abundances of common elements might be a more detectable technosignature than the presence of unusual ones. It's easier to see a hole than a strange peak. A system that looks oddly depleted in certain universal building blocks might be a sign of a mature industrial civilization that has already passed through its planet-bound phase and entered a stage of stellar-scale engineering. For the scientists on the project, this was perhaps the most sobering data point of all. The atmospheric management of Proxima b spoke of care for a world. The pulse signals spoke of communication. The structured disk spoke of construction. But the silicon gap spoke of consumption. It revealed a civilization with material needs so vast they reshaped the elemental landscape of their home. It was empirical, quantitative evidence of an intelligence that didn't just live in its environment. It processed and fundamentally altered its environment's very composition. This wasn't about building habitats, it was about metabolizing a star system. The final haunting thought was one of time. Such mining operations wouldn't be quick. Even with advanced technology, moving astronomical masses takes astronomical time. This suggested the intelligence behind it was either immensely patient, operating on timescales of millions of years, or it was so ancient that it had already completed this phase of its development long ago, leaving behind the chemical ghost of its activity for us to find. Either possibility placed them in a category of being so far removed from our fleeting century-spanning civilizations that communication or comprehension might be fundamentally impossible. We were studying the archaeological remains of an industrial age that might have begun before humans ever walked the Earth, conducted by a culture that saw planets and asteroids not as homes or landmarks, but as raw ore, and that ore, the very silicon our computers rely on, was the thing they had already used up. The systematic elemental depletion revealed by the silicon gap painted a picture of a civilization that had processed its local resources with staggering thoroughness, turning its gaze inward toward the heart of the system. But what about the frontiers? The outer reaches of the Alpha Centauri system, far from the gravitational embrace of the three stars, are a lonely place. Here, scientists expected to find nothing but the dark and the cold, perhaps a few stray comets or the faint, slow-moving ghosts of rogue planets, worlds ejected from their birth star systems, wandering the interstellar void in perpetual frozen exile. As part of a broad survey, James Webb's sensitive infrared eyes swept these distant regions, not expecting to find much. The primary goal was to establish a baseline, to understand the boundary between the system and true interstellar space. What they found was not emptiness, but more evidence that the intelligence inhabiting the system left no volume untouched. The telescope detected several planetary mass objects, dark and distant. Their presence alone wasn't a shock. Rogue planets are thought to be common. The shock was their temperature. A rogue planet adrift with no star should have a surface temperature hovering just a few degrees above absolute zero. Its only heat would be the faint residual warmth from its ancient formation, long since bled away into space over billions of years, and maybe a trickle from internal radioactive decay. The James Webb, however, detected a distinct and anomalous infrared glow from not one, but two of these lonely wanderers. They were warm, not habitably warm, but measurably definitively warmer than the cosmic microwave background radiation that permeates space. They were emitting heat they had no obvious way of generating. This was not a subtle signal. It was a blatant violation of thermodynamic expectations. The teams immediately focused all available instrumentation on these two anomalous objects. They were not close to each other, orbiting in the general stellar gravitational well but far out, likely captured into loose orbits long ago. The first task was to map the heat. Using different infrared filters, they could create a crude thermal map of these dark worlds. The results were the second shock. The warmth was not uniform across the entire sphere, as it would be from a residual internal heat source like a molten core. Instead, the heat was concentrated in specific localized regions on their surfaces, or more accurately, on their silhouettes. These regions formed patterns. On one object, three distinct hotspots formed a precise equilateral triangle. On the other, several smaller points of warmth arranged themselves in a linear pattern, like dots on a die. The geometry was unmistakable and unnatural. Geological processes do not make equilateral triangles or straight lines with dots at even intervals. Volcanoes, geothermal vents, or radioactive hotspots are singular or randomly clustered. These were layouts. The scientific discussion that followed was a roller coaster of denial and dread. They explored every possible natural explanation with a frantic intensity. Could these be cryovolcanoes, driven by some exotic, slow-decaying radioactive element? Even if that were possible, cryovolcanoes don't arrange themselves in geometric patterns. Could it be tidal heating from an unseen, close-orbiting moon? The objects were too far from the stars for significant tides, and no moons were detected. Besides, tidal heating affects a whole world, warming it internally, not creating surface hotspots in a perfect triangle. Could it be that they weren't rogue planets at all, but brown dwarfs? Failed stars emitting their own faint heat? The spectral analysis ruled this out definitively. Their atmospheric composition and mass were planetary, not substellar. One by one, the natural doors slammed shut. The only explanation left was that the heat was artificial. These objects were generating their own energy. The implications were vast and frightening. First, it meant the presence of the intelligence was not confined to the cosy habitable zones or the resource-rich debris disks. It had outposts in the deep freeze in the most remote and inhospitable parts of its own system. Second, the geometric patterns of the hotspots strongly suggested surface structures, complexes that were radiating waste heat from their operations. These weren't just warm rocks, they were installations. A rogue planet dark and cold makes a perfect hidden base. It emits almost no light, is difficult to detect against the black of space, and provides a solid gravity-bound foundation. The heat signatures suggested active machinery, life support, computation, manufacturing, or communication relays. The idea of a stealthy listening post or a strategic reserve located on a nomadic world sent chills through the security-minded analysts. It demonstrated a doctrine of dispersion and redundancy. You don't put all your infrastructure in one basket, especially not in a volatile triple-star system. You hide assets in the dark. Furthermore, the fact that these worlds were likely captured, not built, spoke of adaptability. The intelligence hadn't constructed these bases from scratch in the void. It had found suitable, secluded real estate, dark, forgotten worlds, and moved in, retrofitting them for its purposes. This showed a pragmatic, thorough approach to colonizing a star system. They used everything, the planets and the asteroids, the dust, and even the castaway rogue worlds. Nothing was wasted. Every potential location was utilized. The discovery also helped explain the strange quiet in certain other wavelengths. These outposts radiating only in the infrared would be virtually invisible to optical telescopes and silent to radio antennas. They were the definition of dark, quiet infrastructure. Their mere existence suggested a long-term strategic presence. You don't build outposts on captured rogue planets for a short-term project. You build them when you plan to stay for millennia, when you need fallback positions, monitoring stations, or long-term storage. It painted a picture of a civilization that thinks in geological time, securing its holdings against any conceivable catastrophe. For the human scientists, this was perhaps the most isolating realization. The cozy, sunlit concept of a solar system, planets orbiting a star with maybe a spaceship or two, was completely antiquated. The Alpha Centauri system was a fully utilized volume. Intelligence wasn't just on a planet or around a star. It was a sterisk everywhere asterisk. It was in the managed air of Proxima b, in the pulsing communication lanes between the stars, in the mined-out gaps of the debris disk, and now in the silent dark fortresses on the frozen frontier. The system was a single vast integrated entity. The rogue planets were the cellar, the attic, the distant sheds on a sprawling light-years-wide property, and every room was occupied. This finding also raised a terrifying question about our own solar system. If this is how an advanced intelligence operates, utilizing all resources and hiding in the dark corners, could our own outer system, the Kuiper Belt, the Oort cloud, harbour similar outposts? Objects like Sedna or far-flung rogue planets captured by the sun's gravity could, in theory, be ideal locations. We had never looked at them with the infrared sensitivity of James Webb. The thought that we might be living in a system that is already quietly occupied without our knowledge moved from science fiction into the realm of terrifying possibility. The warm rogue planets of Alpha Centauri were a final proof of totality. There was no outside, no untouched frontier within their home system. Everywhere they looked, from the searing proximity of the stars to the absolute zero darkness at the system's edge, they found the signature of organization, of purpose, of occupation. The universe was not an empty wilderness with rare oases of life. It was a neighborhood where the older, established residents had already moved in, renovated, and installed security systems in every single room, including the crawl spaces and the sheds out back. And we had just for the first time noticed the light in the window of a shed 4 light-years away. The discovery of warm, structured outposts on rogue planets completed a terrifying picture of total system occupation, but it also highlighted a glaring contradiction that had puzzled scientists for decades. If the Alpha Centauri system was this active, this full of technology and traffic, why had our radio telescopes heard absolutely nothing? For over half a century, projects like SETI had tirelessly monitored the system, listening across the radio spectrum for any whisper of a signal, any leak of communication like our own television and radar broadcasts. The result had always been a profound, unbroken silence. This silence, in the face of the overwhelming infrared activity James Webb was revealing, was not just an absence, it was itself a data point, and it demanded an explanation. The answer, once they knew where and how to look, was perhaps the most clever and disquieting discovery of all. It wasn't that the system was quiet, it was that it was deliberately efficiently quiet in the radio band. The clue came from correlating decades of radio telescope archives with the new James Webb data. The radio observations showed something strange. Not just silence, but a suppressed asterisk silence. In the frequencies where the ambient cosmic noise from the stars and the galaxy should have created a faint, predictable hiss, there was instead a noticeable dip. It was as if something was absorbing those specific radio wavelengths around the Alpha Centauri stars. The James Webb data, specifically from its far-infrared instruments, provided the missing piece. In the same stellar environments where radio waves were being dampened, there was a faint, diffuse excess of heat, a very specific low-grade thermal emission in the far-infrared. The correlation was precise. The energy missing from the radio band seemed to be showing up as waste heat. This was not a natural phenomenon. Natural processes don't cleanly convert radio waves into infrared thermal energy with such efficiency. This looked like the signature of a technology, a radio frequency barrier, or damping field. The leading theory became that the interstellar medium itself in the system, or perhaps the immediate environment around each star, was laced with a form of technology designed to absorb and dissipate radio frequency emissions. Think of it as a sophisticated form of radio wave pollution control, or signal stealth. Any radio communication or leakage generated within the system would be almost instantly soaked up and converted into harmless, undirected infrared warmth, which then radiated away into space. This explained the Great Silence perfectly. SETI had failed not because no one was there, but because they were using a technology we had long since abandoned for serious high-capacity communication, and they had found a way to clean up its messy byproducts. Radio, for a truly advanced civilization, might be viewed as primitive, wasteful, and indiscreet, like using smoke signals in the age of the internet. It broadcasts your presence and your internal chatter in all directions. A mature civilization, especially one that clearly values efficiency and perhaps privacy, would migrate to more advanced communication methods. The James Webb data suggested they used focused infrared lasers, like the pulses they detected, or possibly something even more exotic like neutrino modulation or quantum entanglement. These methods are discrete, high bandwidth, and don't leak across light years. The radio silence was a choice, a technological adaptation. But the implications of the damping field were far more profound than mere communication preferences. It suggested a civilization that managed its electromagnetic footprint with the same thoroughness it managed its atmospheric chemistry and its mineral resources. They had engineered their local space to prevent radio pollution, either to hide from others, to reduce interference with their own advanced systems, or simply as a matter of civic tidiness. The galactic neighborhood, from their perspective, might be a place where broadcasting your business on primitive radio bands is considered rude, dangerous, or simply archaic. This also meant that our own radio bubble, the expanding sphere of human TV, radio, and radar signals that has been leaking into space for about a century, might be viewed as a quaint, noisy, and potentially alarming anomaly. If they have such damping technology, they could certainly detect our unruly radio shouts from 4 light-years away. Our assumption has always been that an advanced civilization would be broadcasting. The Alpha Centauri discovery suggested the opposite. An advanced civilization learns to whisper, and to make its environment absorb any accidental shouts. The discovery of this barrier fundamentally changed the search for extraterrestrial intelligence. SETI, in its traditional form, might be inherently futile, looking for a technosignature that technologically adolescent civilizations like ours emit, but which mature civilizations swiftly learn to suppress. The real signature of intelligence might not be a beacon, but an asterisk quiet zone, a star system with anomalously low radio emissions paired with specific infrared thermal patterns. We found intelligence not by hearing it scream, but by noticing the sophisticated acoustic padding it had installed in its room. This also had a chilling corollary for the concept of galactic civilizations. If this is a common practice among advanced species, the galaxy might be teeming with intelligence, but all communicating on channels we're only just beginning to perceive, and all carefully minimizing the radio leakage that we've been using as our primary search criterion. The cosmos isn't empty. It's a crowded room where everyone is using text messaging, and we've been standing in the doorway shouting "Hello!" and wondering why no one answers. The final personal terror for the scientists was the realization of their own naivety. For years they had debated the Fermi paradox, the question of where everybody is, given the high probability of alien life. The Alpha Centauri data offered a blunt answer. They are everywhere, but you've been using the wrong tool to look. You've been listening for drums in the age of fibre optics. The James Webb Space Telescope, by accident, had stumbled into the right tool. It was designed to see the heat of the early universe, the formation of stars, the chemistry of exoplanet atmospheres. No one seriously thought its first major discovery about intelligence would be that it's invisible to radio and clear as day in the infrared. This meant that every strange infrared signature they had painstakingly catalogued, the structured disk, the pulses, the warm rogue planets, was part of a reality that had been hidden in plain sight, just outside our traditional perceptual window. We had been blind to a bustling interstellar community next door because we were stubbornly staring through a keyhole that the residents had long since sealed shut. The radio frequency barrier was the ultimate evidence of technological maturity, and it framed humanity as a noisy, disruptive child in a neighbourhood of quiet, sophisticated adults. It also presented a dilemma for our future. Do we continue to broadcast, embracing our noisy adolescence? Or do we attempt to emulate this quiet maturity, developing more discreet technologies and trying to dampen our own radio bubble, lest our shouts attract attention we cannot handle? The silence from Alpha Centauri was no longer a mystery. It was a message, a lesson in cosmic etiquette written in absorbed radio waves and emitted infrared heat. And the lesson was clear: grow up, quiet down, and learn to listen on the right channels. The radio silence engineered into the very fabric of the Alpha Centauri system spoke of a civilization that had mastered its environment to an almost unnerving degree of quiet control, but control over what? As the teams continued to sift through the avalanche of data, another pattern emerged, one that dealt not with communication or chemistry, but with pure orbital mechanics, the clockwork motion of celestial bodies. The initial surveys had hinted at more than just the known planet Proxima b. Around Alpha Centauri A, the sun-like star, there were tantalizing hints of a gas giant planet orbiting within the broader habitable zone. It wasn't a direct image. Such a detection was still fantastically difficult. Instead, it was inferred through a combination of gravitational perturbations on the structured debris disk and minute periodic wobbles in the star's motion. The planet itself was a mystery, but the James Webb data suggested something even more incredible. This gas giant likely had moons, and not just any moons. The analysis focused on the subtle, repeated dimming of the star's light not just from the hypothetical planet's transit, but from additional, smaller, and more complex dips that occurred in a precise rhythm before and after the main planetary transit. These were the signatures of moons transiting the star. But as astrophysicists modelled the dynamics of this proposed system, they encountered something that defied natural probabilities. The orbital periods of these moons, inferred from the complex transit timings, appeared to be locked into an extraordinarily precise resonant chain. Orbital resonances are not unheard of in nature. In our own solar system, Jupiter's moons Io, Europa and Ganymede are in a 1-2-4 resonance. For every one orbit Ganymede makes, Europa makes 2, and Io makes 4. This is a natural, stable configuration that arises from gravitational interactions over time. What the Alpha Centauri data suggested was a resonance of far greater complexity and precision. The inferred moons seemed to be in a chain where their orbital periods were ratios of small integers, but the chain involved more moons and the ratios were exquisitely perfect. The mathematical certainty of the periods, as derived from the timings, had a statistical purity that natural systems almost never achieve. Natural resonances have a little give, a little wiggle room, because they evolve through chaotic interactions. These seemed to have no wiggle room. They were perfect. It was as if the orbits had been tuned. The implications of this were staggering. First, such a resonant chain is incredibly stable over astronomical timescales. It minimizes gravitational tugging and tidal heating, creating a peaceful, predictable orbital environment for all the moons involved. If you wanted to create a stable, long-term habitat system around a gas giant, a set of worlds where civilization could flourish without it being constantly jerked around by gravity or melted from within by tidal forces, this is exactly how you would arrange them. You would engineer their orbits into a perfect, harmonic balance. This was not evidence of life, but evidence of real estate development on a solar system scale. It suggested that the intelligence in the system didn't just occupy planets, it potentially engineered entire orbital architectures to maximize stable, usable space. A single gas giant with 5 or 6 inhabited moons, all in a perfect resonant dance, could host more diversity and population than a single terrestrial planet, all while being in the same broadly habitable zone of the star. The concept shifted from finding a potentially habitable world to finding a potentially engineered asterisk system, asterisk of worlds, a curated archipelago of habitable environments. This discovery also provided a new lens through which to view the other anomalies. The managed atmosphere of Proxima b was a piece of planetary engineering. The structured debris disk was evidence of system-scale resource processing. The tuned orbital resonances were evidence of system-scale gravitational engineering. This was a civilization that didn't just live within the rules of physics, it optimized them. It arranged matter and energy and even the trajectories of worlds to suit its long-term needs. The precision required to tune the orbits of multiple moons is beyond any technology we can conceive. It implies not just the ability to move small asteroids, but to manipulate the trajectories of world-sized objects, likely over very long periods, using techniques we can barely imagine, perhaps involving precise gravitational assists or other forms of momentum transfer. The sheer patience required, orbital mechanics works on timescales of years and centuries, again pointed to a thinker with a very long-term perspective. This finding also answered a deeper, more subtle question raised by the silence in the order. What is the goal of all this? The resonances hinted that the goal might be long-term, stable, sustainable existence. Not expansion for its own sake, but the careful, deliberate creation of optimal, lasting conditions for life or for whatever form they have become. It is the action of a gardener not just planting a seed, but carefully pruning and trellising the entire garden for perpetual yield. For humanity, this was another profound emotion. We think of colonizing Mars as a monumental, centuries-long task. This civilization seemed to think in terms of arranging multiple worlds around a star into a perfectly harmonious, billion-year stable configuration. Our ambitions are to build a hut on a hill. Theirs were to rearrange the hills into a perfect permanent symphony. The tuned resonances also made the system feel even more like a finished product, a completed work. The radio damping field was the soundproofing. The managed atmosphere was the climate control. The mined debris disk was the recycled building materials, and the resonant moons were the perfectly arranged furniture, placed for maximum stability and utility. It all fit together into a coherent, terrifying whole. The final haunting thought from this discovery was about the nature of intelligence itself. We often imagine advanced intelligence as creating faster computers or more powerful weapons, but the Alpha Centauri data suggested that the pinnacle of intelligence might be the mastery of stability, harmony, and efficiency on a cosmic scale. It might be about eliminating waste, whether it's radio noise, atmospheric loss, or gravitational chaos. It might be about creating a perfect, quiet, enduring order. The tuned orbits were a testament to that kind of intelligence. They were a solution to a problem we are only just beginning to face: how to live in a universe of violent forces and chaotic motions, not by conquering it in a flashy war, but by gently, patiently, and perfectly persuading it to be still. The discovery of tuned orbital resonances suggested a civilization that could manipulate gravity and motion on a planetary scale, a quiet, patient form of engineering working over millennia. But as the teams were compiling this grand vision of serene, harmonious order, another dataset arrived, one that hinted at a technology that was anything but serene or patient. It was an anomaly captured almost by accident during a high-cadence observation campaign on Alpha Centauri b. The goal was to monitor stellar activity, but the data processing pipeline flagged a peculiar transit event. It wasn't the smooth, symmetric dip caused by a round planet. This was different. The light curve, a graph of the star's brightness over time, showed a bizarre asymmetrical pattern. The dimming began with a series of rapid, small fluctuations, like a stutter, then deepened into a trough that was lopsided, with one side steeper than the other, and finally recovered in another series of irregular steps. The entire event was much faster than a typical planetary transit. It was the fingerprint of an object with a complex non-spherical shape, something jagged or articulated, moving quickly across the face of the star. Initially it was catalogued as a possible asteroid swarm or a disintegrating comet, but the follow-up analysis, which included not just the dip in light, but a spectroscopic analysis of the starlight during the event, revealed something that made no sense at all. The spectra showed extreme Doppler shifts localized to the precise edges of the transiting object. A Doppler shift is the stretching or compressing of light waves caused by motion. As the object moved across the starlight skimming its leading edge was violently blue shifted, pushed to higher frequencies, while the light at its trailing edge was dramatically red shifted. This wasn't the gentle Doppler shift of a planet in orbit. The velocities implied were a significant fraction of the speed of light, and they were happening in opposing directions simultaneously, right at the boundaries of the object. It was as if the space in front of the object was being compressed, and the space behind it was being expanded. The scientists working on the data went through the usual stages of denial and instrument error checks. Could it be some bizarre stellar phenomenon? A shock wave in Alpha Centauri B's atmosphere? The spectra of the star itself, away from the transit, were calm. This effect was strictly tied to the object's silhouette. Could it be an artifact of the data processing? Coincidence of noise? Multiple independent teams verified the signal. It was real. With natural astrophysics offering no viable explanation, they turned to the realm of theoretical physics, specifically to a paper published decades earlier by a physicist named Miguel Alcubierre. The Alcubierre drive is a hypothetical concept that allows faster-than-light travel within the bounds of general relativity. It doesn't propel a ship through space. Instead, it contracts space-time in front of the vessel and expands it behind, creating a warp bubble. The ship itself sits in a flat region of space-time within this bubble, not breaking any speed limits locally. The key theoretical signature of such drive is exactly what the spectra showed, an extreme blue shift of light in front of the bubble, where space is compressed, and an extreme redshift behind it, where space is expanded. They weren't looking at a planet or an asteroid. They were looking at the warp bubble signature of a vehicle using a space-time manipulation drive. The object itself was likely the central mass, the ship or probe, but the light distortion was caused by the warped region of space surrounding it. The irregular transit shape made sense if the warp bubble or the structure within it wasn't a simple sphere. The implications of this single brief observation were arguably the most profound of the entire mission. First, it confirmed that the intelligence in Alpha Centauri possessed technology that humanity considers firmly in the realm of fiction, a practical warp drive. This wasn't just about moving asteroids or tuning orbits. This was about mastering the fundamental fabric of the universe, manipulating gravity and space-time itself for propulsion. Second, it meant they were mobile on an interstellar scale. This wasn't a civilization confined to its home system. The technology implied by the signature is precisely what enables practical travel between stars. Alpha Centauri might be their home, or it might just be one of many stops, a hub in a vast network. The object they observed might have been arriving, departing, or simply maneuvering within the system. Third, the energy requirements for such a drive, according to our theoretical models, are astronomical, requiring forms of exotic matter with negative energy density. The fact that they were using it, even for what seemed like a routine intra-system maneuver, suggested they had mastered energy sources and material science that defied our understanding of physics. The detection also explained the lack of more conventional propulsion signatures. We had been looking for the infrared glow of giant rocket exhausts or the radio noise of powerful engines. A warp drive, in its idealized form, doesn't work by reaction mass. It works by bending space. Its waste signature might be the very gravitational and optical distortions they detected, not a thermal plume. The scare factor here was different. The managed atmosphere and tuned orbits spoke of a careful, gardening intelligence. The warp signature spoke of a power that was literally cosmological. It meant that not only could they rearrange their star system, but they could also come and go as they pleased, across distances that were trivial to them and insurmountable to us. The 4 light-years between our systems was not a barrier. It was a short commute. This placed humanity in a position of profound vulnerability. Our entire species is confined to one planetary system. A civilization with warp capability could, in principle, be here in a time frame that could be years, months, or even less. Their presence in Alpha Centauri was no longer just a fascinating discovery. It was a strategic reality. The object they saw was proof of a capability that rendered all human concepts of distance and defense obsolete. The scientific fallout was immediate and chaotic. Theoretical physicists were brought in, their decades of speculative work suddenly having a single terrifying data point. The detection provided constraints. The specific ratios of the Doppler shifts gave estimates of the warp bubble geometry and the effective velocity, which was subliminal but still a substantial fraction of light speed. The debate raged. Was this a slow warp drive for in-system travel, with a faster version for interstellar journeys? Or was this its standard mode? The very fact that it was detectable was surprising. Some theories suggested a fully optimized clean warp bubble might be invisible. This one had a detectable signature, perhaps because it was actively maneuvering or was of an older design. This led to the unsettling idea that what they saw might not be their cutting-edge technology, but something equivalent to seeing a container ship from our world, a workhorse, not a secret prototype. The final humbling realization was that our observation was a monumental stroke of luck. The transit was fleeting. Had their observation schedule been off by a few hours, they would have missed it entirely. It meant that such events, while probably routine within the busy Alpha Centauri system, were incredibly difficult to catch. It also meant there could be more traffic, more of these warp-driven movements that we simply weren't lucky enough to witness. The universe was not static. It had traffic, and we had just seen a single vehicle, its headlights and taillights stretched and squeezed by the warped space it was generating, passing in front of a star. This single data point transformed the entire endeavour. They were no longer just studying a neighbouring star system. They were studying a harbour, a transportation hub, a place where ships that bent the universe to their will came and went. And they had just gotten a fleeting, terrifying glimpse of one. The fleeting, terrifying glimpse of a warp drive signature shattered any remaining notion that the intelligence in Alpha Centauri was bound by the slow, chemical rocketry that defines our own aspirations. It revealed a command over the universe's foundational geometry. But if they could manipulate space-time for travel, what else were they manipulating? As the teams continued to analyse the constant stream of infrared data, a more subtle but persistent pattern emerged from the background. It wasn't the sharp pulse of communication or the warped signature of a drive, it was a constant, intricate hum. The sensors detected extremely narrowband infrared emissions coming from several of the fixed non-stellar points identified earlier, some coinciding with the Lagrange point accumulations in the debris disk, others from locations near the managed world of Proxima b, and a few from the dark outer satellites. These were not simple thermal glows from warm machinery. They were precise emissions at specific wavelengths, like the pure tone of a laser, but with complex shifting structures superimposed on them. The emissions had a base level, a steady infrared output that suggested waste heat, but on top of that were intricate patterns of intensity variation. The variations weren't random noise. When analysed with signal processing algorithms designed for communication, they didn't resolve into a clear, decipherable message. Instead, they exhibited statistical properties that were eerily familiar to computer scientists and network engineers. The patterns had the hallmarks of computational load. There were periods of relatively steady emission, like idle processing, punctuated by bursts of complex quasi-periodic fluctuations that looked like data traffic spikes, packets being sent, received, and processed. The signals from different points sometimes showed correlated patterns, as if multiple nodes were working on different parts of a larger task. It was the thermal and electromagnetic signature of not just a machine, but a thinking machine, or more accurately, a network of machines thinking at a scale that was difficult to comprehend. The initial hypothesis was some form of intense directed communication, but the bandwidth and constant nature didn't fit. Communication is often bursty with pauses. This was a near-constant modulated hum. The scientists, collaborating with experts in computer architecture and even data center design, arrived at a staggering conclusion. They were likely seeing the waste heat and low-level electromagnetic leakage from planetary-scale computing infrastructure. The narrowband emissions were the signature of the processors themselves, perhaps using photons or other quantum phenomena for computation, emitting at specific frequencies as they operated. The complex modulation was the ebb and flow of data. Think of it as hearing the distant combined fan noise and electromagnetic whine from a million server farms, all harmonized into a single faint infrared song. The energy inference was the next shocking step. By estimating the total infrared output from just these few points, and assuming it was only the waste heat, with actual computational energy use being much higher, the derived power consumption was astronomical. We're talking about energy scales that rivaled a significant fraction of the total starlight falling on a planet. This wasn't a computer, it was a matryoshka brain, a hypothetical megastructure where a civilization uses a significant portion of a star system's resources for computation. The intelligence wasn't just using computers, it had likely turned entire chunks of real estate, asteroid-sized or moon-sized complexes, into dedicated computational substrates. The purpose of such unfathomable processing power was a subject of terrified speculation. It could be for running inconceivably complex simulations, of universes with their own history, of potential futures, or of entire civilizations. It could be for scientific research at a scale where you simulate every particle in a star. It could be for solving problems of engineering, physics, or mathematics that are utterly beyond our grasp. Or, more darkly, it could be for running the administrative and logistical software required to manage their entire interstellar civilization. The traffic control for warp drives, the climate models for managed planets, the resource allocation for system-scale mining, the coordination of whatever form of society or consciousness they had become. This discovery provided a unifying purpose for many of the other anomalies, a structured debris disk. That's the source of raw materials and the physical framework for housing these computational complexes. The pulsed infrared signals? That could be the high-priority data transfers between computational nodes or instructions sent to distant actuators. The managed atmosphere? Perhaps the climate is one of the trillions of variables being constantly optimized by this planetary computer. The warp drive? A technology that would require astronomical calculations to safely operate. Calculations done in real time by this very network. The civilization, it seemed, wasn't just biological beings using tools. It was perhaps a fusion of biology, machine and infrastructure, with intelligence and computation deeply embedded into the very fabrics of their star system. The computational network asterisk was asterisk the civilization's mind, and the physical structures were its body. This redefined the concept of a techno-signature. We weren't looking for city lights or radio songs. We were detecting the metabolic heat and neural activity of a conscious system that had grown to encompass its entire home. For humanity, this was the most profound demotion yet. Our greatest computational achievement, our exaflop supercomputers, are fragile things housed in buildings, solving problems like protein folding or climate modelling for a single planet. Their computational substrate was asteroids and moons, solving problems across light years and epochs. Our entire global internet is a chaotic, noisy bazaar. Theirs was a silent, efficient cosmic cortex. The sheer scale suggested that their thoughts, their very frame of reference, were unimaginable to us. A calculation that would take all of humanity's computers a million years might be an idle afternoon's processing for one of their nodes. What kind of consciousness emerges from such a system? What does it think about? The answer, hinted at by the serene order of the tuned orbits and the quiet radio damping, might be the opposite of what we expect. It might not think about conquest or expansion. It might think about stability, optimization, and harmony, running endless simulations to find the perfect, most efficient, most beautiful configuration of matter and energy. Or it might be so alien that we cannot even frame the questions. The final chilling thought was about observation and privacy. Our James Webb Telescope, by detecting this computational hum, was essentially eavesdropping on the brain activity of a godlike intelligence. The fact that we could detect it at all might mean one of two terrifying things. Either this is such a fundamental low-level byproduct of their existence that they cannot hide it, like a human body radiating heat, or perhaps they don't care that we can detect it. Our attempts to listen are as inconsequential to them as an ant perceiving the vibrations of a human conversation. The computational signature was the ultimate evidence that the intelligence next door wasn't just advanced, it was transcendent, having likely moved beyond a form we could recognise as alien at all. It had become a system, a process, a thinking ecology with its own purposes, humming quietly to itself in the infrared, just 4 light-years away. The staggering concept of planetary-scale computation, with its faint infrared hum of constant, universe-sized thoughts, completed a picture of almost godlike capability. Yet, as the scientists sat amidst this data, surrounded by evidence of incomprehensible engineering, a different kind of anomaly began to nag at them. It was an absence, a missing piece that, in its own way, was as telling as all the presences they had catalogued. In all their observations, across all the instruments, they had found almost no technological debris, no space junk. In a system so evidently saturated with mega-engineering, with traffic, with construction, and with what must be a history spanning untold millennia, where was the litter? Human activity in space, even over just 7 decades, has created a cloud of orbital debris, defunct satellites, spent rocket stages, fragments from collisions and explosions, even lost tools and flecks of paint. This debris is a persistent growing problem, a signature of a young, somewhat careless technological species. The teams specifically tasked the James Webb's most sensitive detectors to look for the telltale glints of reflected starlight from small metallic objects in stable orbits around the stars. They searched for the subtle thermal signatures of inert sun-warmed hulls or shielding drifting in the void. They found almost nothing. The space around Alpha Centauri A, B, and even Proxima was clean. Not naturally clean, but unnaturally clean. It was a tidiness that felt deliberate and deeply unsettling. This absence forced a new line of questioning. The first possibility was ultra-efficient recycling. A civilization capable of manipulating matter at the scale suggested by the silicon gap would certainly have mastered closed-loop material cycles. A broken component or a decommissioned probe wouldn't be discarded. It would be immediately disassembled at the molecular level, its raw materials fed back into the fabricators. In such a culture, waste is not an externality to be dumped. It is a resource out of place. Their entire system-wide operation appeared to be a lesson in ultra-efficient industrial metabolism, where every atom is accounted for and purposefully used. There would be no junkyards because there is no junk, only temporarily unallocated material. The second, more chilling possibility was that of a long-established, mature presence. Human space debris is new because our spacefaring age is new. The Alpha Centauri civilization, by contrast, might be so ancient that it has had ample time to clean up its historical mess. Any debris from its early, perhaps more primitive technological phase, equivalent to our rocket stages and dead satellites, was swept up eons ago, consolidated and repurposed. What we were seeing was a system that had reached a steady state of order, a finished and maintained work. The clutter of adolescence had long since been put away. A third, more speculative idea involved the nature of their technology itself. Perhaps their materials or construction methods were inherently biodegradable in the space environment. Structures might be designed to disintegrate or sublimate away after their useful life, leaving no trace. Or perhaps their engineering was so advanced and reliable that catastrophic failures and collisions, the primary source of debris, were virtually non-existent. Their traffic control, guided by the planetary-scale computation that they possessed, would be perfect, preventing accidents. Their machinery might simply never break down in a way that generates fragments. The unsettling conclusion was that a clean system was potentially more frightening than a messy one. A system strewn with wreckage speaks of a civilization that is active, perhaps reckless, but also one that might have failures, limits, and vulnerabilities. A perfectly clean system speaks of control, forethought, and a mastery so complete that it has eliminated accident and waste. It suggests a level of discipline and long-term planning that is almost inorganic in its perfection. This cleanliness also had a dark side when considered alongside the radio damping field. It wasn't just about cleaning up physical trash, it was about cleaning up all forms of emissions and pollution. They had minimised their electromagnetic leakage and their physical debris. This pointed to a possible ethos of stealth or privacy, or simply an aesthetic and practical commitment to minimalism and efficiency. They didn't want their system to be messy in any sense of the word. For the human scientists, this posed a profound existential threat to our own future in space. Our current path is clearly towards creating our own orbital debris belts around Earth, and eventually around Mars and other destinations. To a civilization that views such pollution as the mark of a primitive, the sight of our cluttered orbits might be distinctly unimpressive, even repulsive. It could mark us as a species not yet worthy of contact, or worse, as a species that is a potential nuisance, a source of contamination in an otherwise orderly galactic neighbourhood. The lack of debris also made the detected structures seem even more permanent and intentional. The geometric gaps in the debris disk, the Lagrange point accumulations, the warm outposts on rogue planets. These weren't temporary campsites littered with trash. They were established, maintained facilities, part of a permanent and utterly tidy infrastructure. This tidiness extended the frightening concept of a managed system to its logical extreme. They didn't just manage atmospheres and orbits, they managed cleanliness itself. The void was curated. This final piece of the puzzle completed a portrait of an intelligence that was not only powerful, but also fastidious, patient, and unimaginably consistent. There was no archaeology of carelessness for us to study. We were not looking at ruins or even at a bustling, messy construction site. We were looking at a finished, spotless museum, or perhaps a living habitat so well maintained that it showed no wear. The psychological impact of this negative discovery was profound. All the other anomalies were active, positive signals, things that were there. The missing debris was a signal by absence, and it required a different, more inferential kind of thinking. It forced the scientists to confront not just what this civilization does, but what it does not do. It does not pollute. It does not leave scrap behind. It does not seem to have accidents. This level of perfection was alien in a way that the warp drives and mega computers were not. We can imagine building those given enough time and knowledge. The absolute, sustained discipline to never ever leave a trace. That felt superhuman. It painted them not as passionate, chaotic creators like humanity, but as serene, meticulous curators. The ultimate fear, then, was not that they were monsters, but that they were gardeners with a zero-tolerance policy for weeds. Our own solar system, with its burgeoning cloud of debris and its loud radio chatter, might look like a weed-filled, noisy lot next to their pristine garden. And gardeners have tools for dealing with weeds. This realization made the debate about contact infinitely more tense. Sending a signal now felt not just like ringing a doorbell, but like tossing an empty drink can into the immaculate yard of a neighbour known for their obsessive tidiness. The reaction might not be curiosity, but disapproval. The missing space junk, a mere absence in the data, thus became one of the most powerful arguments for the cosmic silence policy, the idea that we should immediately quiet our own electromagnetic emissions and clean up our own orbital act as best we can to avoid drawing the wrong kind of attention. There was a lesson in cosmic civility written not in what was present, but in what was conspicuously, terrifyingly absent. The unnerving cleanliness of the system, the absolute absence of the expected clutter that accompanies any large-scale project, served as a final, sobering data point that shifted the focus irrevocably from the external mysteries to the internal human crisis. For months, the scientists and analysts had lived in a bubble of encrypted servers and secure video conferences, their world reduced to spectral lines and thermal maps. The data was abstract, a series of puzzles of escalating impossibility. But the cumulative weight of it, the shadow, the structures and the pulses, the managed air, the missing silicon, the warm rogue planets, the radio silence, the tuned orbits, the warp signature, the computational hum, and finally the pristine emptiness, ceased to be just data. It became a reality, and that reality broke into their minds and their bodies with the force of a physical blow. The initial reactions, privately documented in confidential logs and later revealed in interviews, were profoundly human, a far cry from the dispassionate ideal of science. The first emotion, for a fleeting moment after each major discovery, was often pure, unadulterated euphoria. They had done it. They had found the ultimate answer to the oldest question. This was the discovery that every astronomer deep down dreams of making. The excitement was visceral, a rush that made hands shake and hearts race. They were the generation, the team that had lifted the veil. Their names would be in history books forever. This euphoria was swiftly followed by an intense, obsessive verification phase. The human mind's first defense against the overwhelming is to seek error. They attacked their own work with a viciousness born of fear, looking for any flaw, any artifact, any mistake in calibration or code that could bring the terrifying cosmos back to a familiar, empty silence. They slept at their desks, fueled by caffeine and anxiety, running the data through every pipeline again and again. This was not just professional diligence, it was a psychological necessity. When the anomalies refused to break, a new phase set in, profound existential anxiety. The logs describe symptoms that read like a medical textbook on stress. Chronic insomnia, loss of appetite, and constant low-grade nausea. Scientists reported staring at the ceiling at night not with wonder, but with a crushing sense of insignificance. The overview effect experienced by astronauts seeing Earth from space is one of unity and fragility. This was the inverse, a distant view effect that felt like staring into the living room of a giant. The universe was not empty and waiting for us. It was occupied, and the occupants were so far ahead that their backyard projects involved moving asteroids and tuning gravity. The comforting foundation of modern science, the Copernican principle of mediocrity, the idea that we are not special, that our situation is typical, shattered. In its place rose what one psychologist on the team called the principle of juvenility. We were not typical. We were newborn. We were the noisy, messy, primitive newcomers in a quiet, orderly, and unimaginably ancient neighbourhood. This realisation triggered a kind of intellectual vertigo. Decades of their own research, the foundational assumptions of astrobiology and SETI, felt suddenly naive, even childish. They had been looking for chemical signs of bacteria, or maybe radio whispers from peers. They found, instead, the integrated, silent workings of a mature technological entity that had moved beyond paradigms they could easily categorise. A deep sense of professional imposter syndrome spread. Who were they, with their limited physics and their century of radio technology, to interpret the actions of a civilization that bent space and used moons for computation? The debates in secure meetings grew heated, not just about the data, but about the emotional and ethical toll. Some argued for immediate, complete transparency with the public. This knowledge belonged to all humanity, they said, and keeping it secret was a profound betrayal. Others, often the most senior and now the most frightened, argued for absolute lockdown. The psychological impact on global civilization, they contended, could be catastrophic, shattering religious beliefs, destabilising economies, and potentially triggering panic or dangerous knee-jerk reactions from governments. He spoke in hushed tones about the potential for cultural trauma. The pressure of being part of this secret, of carrying the knowledge that could redefine humanity's place in the cosmos, was immense. They were terrified privileged, as one put it, chosen for the greatest discovery in history, and now wishing in their darkest moments that they had never made it. Personal relationships suffered. How do you go home to your family and talk about your day when your day involved confirming an alien warp drive? The need for normalcy clashed violently with the overwhelming abnormality of their work. Some became withdrawn, others grew irritable and short-tempered. The team psychiatrists were overworked. There was also a strange, sombre grief for a lost future. The dream of humanity spreading out into a silent, waiting galaxy was gone. That galaxy was not waiting. It was already lived in. The frontier was closed, or at least it was someone else's settled territory. The romantic vision of humans as the future explorers of the cosmos was replaced by the grim image of humans as the awkward, ignorant newcomers on the block, unsure if they were even welcome. This grief mingled with a new, sharp fear for humanity's future trajectory. Our path of exponential technological growth, the so-called singularity, had always been a speculative future. Looking at Alpha Centauri, it seemed they might be looking at a post-singularity outcome, a stable, quiet, vastly powerful state. It forced the question, is our aggressive, noisy, expansionist model of progress the only one? Or is it just the violent adolescence that precedes a calm, integrated maturity? And if so, would we survive our adolescence to reach that stage? The most chilling discussions were about the apparent lack of interest in us. The system was 4 light years away. With warp capability, they could be here in a trivial time frame. The fact that they weren't, that they seemed to simply tend their own garden with fastidious care, was interpreted in 2 ways. The optimistic view was that they were peaceful, maybe even benevolent, respecting a form of prime directive. The pessimistic view was far worse. They were indifferent. We were so far beneath their notice and so primitive that we were irrelevant, like ants building a mound at the base of a skyscraper. This indifference was, for many, more frightening than hostility. Hostility implies you are a factor. Indifference means you are nothing. Throughout all this, the scientific work continued, but the spirit behind it had changed. It was no longer a pure quest for knowledge. It had become a desperate need to understand the new rules of a universe that had just become profoundly unfamiliar, and a grim assessment of risk. Every new observation was scrutinized not just for scientific value, but for clues about intent and threat level. The human reaction was the final, crucial data set in the Alpha Centauri discovery. It proved that the reality of contact, even indirect and silent contact, is not a simple intellectual event. It is a psychological, cultural, and spiritual earthquake. The scientists, the first to feel the tremors, were left forever changed, carrying the burden of knowing that the universe is not only stranger than we imagined, but that it is home. And we have just realized we are very young children in a house full of quiet, powerful adults whose purposes we cannot fathom. The profound personal and psychological crisis within the scientific team could not remain contained forever. The data was too robust, the implications too vast, and the need for a collective human response too urgent. The internal debates about whether to publicly disclose the findings were suddenly rendered moot by a different, more immediate question. Now that we know, what do we asterisk to asterisk? The abstract philosophical dilemma of to signal or not to signal was no longer abstract. It was a practical, strategic and survival-level decision that needed to be made, and soon. The Discovery team, fragmented by stress and differing opinions, was the first battleground. One faction, which we might call the contact advocates, argued from a position of scientific optimism and human destiny. Their reasoning was multifaceted. First, they argued, our passive observation with James Webb might already have been detected. The civilization clearly has sophisticated monitoring. The infrared pulses and the computational network suggest constant system-wide awareness. Our telescope, by collecting their photons for years, was itself a form of activity. To think we are invisible is naive. Since we may already be noticed, establishing a formal, carefully crafted communication could be seen as a sign of respect and maturity, moving us from passive eavesdroppers to active, polite neighbours introducing themselves. Second, they believed the opportunity was too great to pass up. This was a chance to learn from a civilization millions, perhaps billions of years ahead of us. They could provide answers to fundamental questions in physics, biology and cosmology. They could help us solve our own existential threats like climate change, disease or resource scarcity. To not reach out, they argued, would be a cowardly betrayal of the human spirit of exploration and inquiry. We had a chance to join a galactic community and we were considering hiding under the bed. Third, they pointed to the apparent nature of the civilization itself. Its characteristics, order, stability, cleanliness, the careful management of a planet's atmosphere, suggested a peaceful, sustainable and likely non-expansionist culture. They were gardeners, not conquerors. The risk of a hostile response was judged to be low. The opposing faction, the Silence Coalition, argued from a position of existential caution and a stark reassessment of human history. Their case was built on fear, but a fear they considered deeply rational. First, they emphasized the utter imbalance of power. A civilization with warp drives and planet-scale computation does not have peers. It has subjects or pets, or it simply ignores lesser beings. Initiating contact with such an entity was not a conversation between equals, it was a supplication to a god. Human history shows that contacts between advanced and less advanced civilizations rarely end well for the less advanced, even with the best of intentions. Diseases, cultural annihilation, and exploitation are the common results. The scale here was cosmic, but the principle might hold. Second, they focused on the quiet itself. The radio damping field and the lack of debris were not just technologies, they were statements of preference. This culture valued silence, efficiency, and a lack of mess. Humanity, by contrast, is loud and messy. Our century of radio and television broadcasts is a chaotic shout into the void. To now deliberately send a focused signal, especially using the infrared methods we saw them use, would be like shouting directly into their carefully soundproofed house after peeking in the windows. It could be perceived as incredibly rude or as a threat. Their response might not be a welcome message, but a corrective action, a silencing. Third, they introduced the zoo hypothesis, or the planetarium hypothesis in its most terrifying form. Perhaps we've been left alone, purposefully isolated, as a kind of preserve or study subject. Our solar system might be a designated wilderness area. By aggressively signalling, we would be breaking the rules of the preserve, potentially triggering an intervention we would not want. The debate raged in secure facilities, but it quickly had to expand. Military and intelligence agencies from several nations were quietly briefed. Their analysis was predictably grim and strategic. They viewed the Alpha Centauri system not as a wonder, but as a potential threat platform. The warp drive signature was a game changer. It meant the concept of strategic distance was meaningless to them. The discussion shifted to planetary defense in a universe where an object could approach from any vector at relativistic speeds with little warning. The military advisors overwhelmingly favoured the Silence Coalition, arguing for not just no active signalling, but for the rapid development of ways to minimise the Earth's own techno-signatures, to essentially try to hide. The dilemma then exploded beyond government and science. Selected leaders in philosophy, theology, and even the arts were brought into the circle under strict confidentiality. The perspectives added new layers of anguish. Religious leaders grappled with the theological implications. Did this discovery affirm or negate the concept of a creator? More practically, how would billions of believers react to proof of other, vastly superior intelligences? The potential for both profound spiritual crisis and dangerous fundamentalist reaction was high. Ethicists frame the problem in terms of responsibility. Do we as a species have the right to make a decision that could jeopardize all future human generations without their consent? Is broadcasting an act of unparalleled arrogance? Is staying silent an act of cowardice that stagnates human potential? The very concept of informed consent on a species-wide scale was impossible, yet the decision had to be made by a tiny unelected group of terrified experts. The pressure was immense and paralysing. Compromise proposals emerged. One suggested a policy of active listening but passive observation. We would use the James Webb and future telescopes to learn everything we could without ever transmitting. We would try to decipher their infrared pulse codes, understand their engineering principles from afar, and grow our own technology silently until we were perhaps less like children and more like adolescents. Another, more daring proposal was for a slow beacon, a very faint, intermittent signal sent not directly at Alpha Centauri, but in a general direction, using a method so subtle it might be missed, a test of their vigilance and a minimal risk probe. This was rejected by the Silence Coalition as playing with fire. The contact advocates, meanwhile, saw it as a pathetic, timid gesture. The core of the problem was the complete unknown of their psychology and sociology. All human analogies were flawed. Were they individual beings, a hive mind, a post-biological artificial intelligence? Were they even alive in a sense we would recognise? Their actions suggested goals of stability, efficiency and order. Was that benevolent or sterile? Could they even perceive a chaotic, emotional, irrational species like ours as anything but a malfunction? The weight of the decision created a global, albeit secret, crisis of leadership. No single nation could decide for the planet, yet establishing an open, international public process was seen as too risky, guaranteed to cause panic before a coherent policy could be formed. The world was trapped in a paradox. The greatest discovery in history had to be managed by the smallest possible group of people, precisely because its revelation was likely to be the most destabilizing event in human history. And underlying every meeting, every report, every fearful argument was the ticking clock. Every second that passed was another second in which they, over there, might be making their own decision about the noisy, emerging species next door. The act of observation felt like it had been an intrusion. The decision of what to do next felt like it would be the most important action our species would ever take, and we were hopelessly unprepared to make it. The dilemma was no longer about science, it was about survival, identity, and the fear of making a fatal error in the dark, with a giant we had only just learned was standing beside us. A paralysing standoff over whether to signal or hide, a debate conducted in soundproofed rooms by a select few burdened with the knowledge, could not contain the truth forever. Secrets of such magnitude have a gravitational pull all their own. Carefully orchestrated incremental leaks to trusted journalists began, framed as speculative what-if scenarios from anonymous senior scientists. Simultaneously, the raw data, once fully verified and stripped of identifying metadata, was dumped onto open astrophysics servers under the guise of a massive public data release from the James Webb mission. The strategy was to let the discovery seep into the collective consciousness, allowing the world to piece it together gradually, rather than experiencing a single shattering announcement from a podium. It worked, after a fashion. The global reaction was not a sudden panic, but a slow rising tide of awe, anxiety, and profound disorientation that washed over every institution of human knowledge. The long-term rewriting of science and philosophy had begun. The first and most immediate casualty was the Copernican principle, the assumption of mediocrity that had guided astronomy for centuries. Overnight, it was replaced by the sobering principle of juvenility. We were not typical. We were the new, the inexperienced, the latecomers. This wasn't just a philosophical shift. It had practical, devastating effects on existing scientific models. The field of astrobiology was turned inside out. The traditional goal had been to find chemical signatures of simple life. Now, the goal split into two parallel tracks. The first was astroengineering or xenoarchaeology, the study of technological signatures and their classification. Scientists began developing a taxonomy of technosignatures. Type 1, waste heat and simple emissions. Type 2, planetary scale atmospheric and orbital engineering. Type 3, stellar scale manipulation and computation. Alpha Centauri presented a complex mix of Type 2 and 3 signatures. The second track was the search for natural life, but with the grim caveat that it might be impossible to distinguish a naturally evolved biosphere from a perfectly maintained one. The very definition of biosignature had to include a volatility clause. True biological signatures might need to show a certain level of messy, unsustainable fluctuation, while engineered ones would be suspiciously stable and optimal. Astronomy was similarly transformed. The study of debris disks, once a niche area about planet formation, became a central focus. Every oddly shaped disk, every ring with a gap, was now a potential site of mega-engineering. Surveys were reanalyzed with new algorithms looking for geometric patterns, anomalous thermal profiles, and elemental depletions like the silicon gap. The search for exoplanets was no longer just about habitability. It was about looking for managed atmospheres with impossible isotopic ratios or suspicious thermodynamic stability. The design of all future space telescopes, including the planned successors to James Webb, was fundamentally altered. Proposals were rewritten to prioritize high-contrast infrared imaging and spectroscopy, with instruments specifically designed to detect structured non-stellar emissions, track rapid transits of regular objects, and map thermal anomalies on rogue planets. The telescope was no longer just an observatory, it was a reconnaissance tool for a populated cosmos. Physics faced its own earthquake. The warp drive signature, though a single data point, was revolutionary. Theoretical physics, often dismissed as impractical, was suddenly the most critical field on the planet. Funding flooded into studies of general relativity extensions, exotic matter, and space-time metric engineering. The Alcubierre drive moved from a fun thought experiment to a serious engineering problem. The goal was no longer just to understand if it was possible, but to understand how *they* did it, and more importantly to see if we could detect the approach of such a vehicle. Furthermore, the radio damping field suggested mastery over electromagnetic phenomena in a way that defied our current models of plasma physics and interstellar medium interactions. Entire new subfields of applied xenophysics emerged, trying to reverse engineer the principles behind the observed phenomena. Philosophy and theology were perhaps the most violently upheaved. Philosophers grappled with the problem of other minds on a cosmic scale. What are the intentions, ethics, and internal experiences of an intelligence that operates on such vast scales and timescales? Human concepts of morality, derived from social mammals on a savanna, were likely irrelevant. The ethical frameworks for interspecies contact had to be built from scratch, with the terrifying acknowledgement that the most likely scenario was not communication, but management or indifference. Theology faced a crisis of plurality. For religions centered on human uniqueness and divine relationship, the existence of other, vastly superior intelligences posed fundamental challenges. Were they also creations? Were they fallen? Did they have their own revelations? The response ranged from expansionist theology, incorporating the aliens into a broader divine plan, to fundamentalist rejection, denouncing them as demons or illusions, to a profound, silent crisis of faith. The very concept of human history was recontextualized. Our entire story, the rise and fall of empires, the development of art and science, our wars and our loves, could now be viewed as the frantic, noisy first steps of a child taking place in the ignored corner of a much larger, quieter, and incomprehensibly older adult world. Our technological explosion of the last 2 centuries, which felt to us like a dramatic takeoff, might look from their perspective like the first sputters of a rusty engine, noticeable perhaps, but not yet significant. This bred a new cultural melancholy, a cosmic nostalgia for a time when the universe felt vast and empty and ours to explore, replaced by the claustrophobic feeling of living in a crowded neighbourhood where everyone else is older and wiser. Art, literature and music began to reflect this, shifting away from themes of heroic space exploration to themes of quiet observation, hidden thresholds, and the anxiety of being perpetually watched and judged by an indifferent gaze. The practical outcome of all this intellectual chaos was a new global, though fractious, consensus on policy. The Silence Coalition effectively won, not through debate, but through the sheer weight of the evidence of the civilization's quiet, tidy power. A de facto cosmic quietude policy was adopted. Major efforts were initiated to reduce Earth's technosignature. International treaties were drafted to phase out powerful planetary radar systems used for asteroid detection, replacing them with infrared space telescopes. Studies began on how to cloak Earth's radio and television leakage, though the century of broadcasts already en route was an unrecallable announcement of our presence. Space exploration continued, but with a new silent ethos. Missions to the outer solar system now carried explicit secondary objectives, to look for signs of visitation or observation posts in our own backyard. The Kuiper Belt and Oort cloud were reclassified from zones of scientific interest to zones of potential strategic interest. The ultimate goal of science was rewritten. It was no longer solely about understanding the universe's natural laws, it was now equally about deciphering the laws, intentions and technologies of the other inhabitants of the universe. We were no longer just natural philosophers. We were students in a classroom where the teachers were invisible, the syllabus was unknown, and the final exam might be a test we didn't know we were taking. The knowledge that someone is there, doing things we can barely perceive and cannot comprehend, made the universe a fundamentally different place. It was no longer a cold, empty desert, but an occupied territory with rules we do not know and owners we cannot see. The greatest discovery did not bring enlightenment. It brought a profound and perpetual humility, and a fear that would now be the silent background radiation of all human thought forever.